All right, so in this video, we're going to be going over exercise 5 from the first practice test, right? And it has to do with transformations and checking if they're linear and if they're a bijection, right? So what we're going to do is, like start off with A, go over a couple of the concepts if we need to, and then move on to B, right? And maybe discuss some of these concepts too, right? So, okay, so what is A asking for? It's asking, is this transformation T a linear transformation? So what the heck is even a transformation to begin with, right? Well, it's kind of like a function, right? You know how we have typical functions that take in numbers, right? And they output something, right? What this is going to do is it's going to take in, so like this transformation is going to take a vector x that's from R3, right? And transform it, right? Into an output vector, right, from R3, right? This one just so happened to be R3 from R3, but you can have like R2 to R4 if you really wanted to, really from whatever dimension you feel like, right? Because whoever's making the function or the transformation really has that control. So whoever made this decided to take a vector from R3 and transform it into another vector from R3, right? So it's just taking in that vector and giving you a vector back, a different vector though, right? At least most of the time. If you put a zero vector into here, then you get a zero vector out, but that's beyond the point, right? We're checking to see if this is a linear transformation. So what does that entail, right? There's actually two ways of going about this, right? There's two ways to check if a transformation T is linear. One of them is going to be really quick. The other one will be not as quick, but they're both going to be easy, right? So let's go over those, like how we're going to go about this, right? So in order to do A, we ought to verify one of the two. So you get two options, right? Option number one is this, right? You have to verify that t of x plus t of y is equal to t of x plus y, right? So, and then in addition to that, you would also have to verify that k t of x is equal to t of kx, right? So this whole thing, the both of these conditions, I should probably put like an ampersand here, are part of the same like sort of like option, right? So that's option number one. Option number two is this. If you have a transformation T of x, which we do, and we can set it equal to some matrix A times x, then like if we can find this matrix A, that's enough to actually prove that T of x is linear, right? So this one, every day of the week is just going to be like so much easier, so much faster, right? Not to say that this isn't easy, right? It's not the worst thing in the world, but this will actually going this route will actually help us for part B, right? That being said, it's what is it? It's May 19th right now. We haven't actually gone over linear transforms right in the class yet, so I don't know which one your professor is going to prefer, right? In my experience, most professors would actually prefer you go this route just to really see that you know what you're doing. But two is just as valid, and it's honestly better if I were in a test, if this is allowed. But that's neither here nor there. We're actually going to go with both, right? Just to get you guys more experience with this kind of stuff. So we're gonna do one, and then we're gonna do two, and then we're gonna go on to B. Right? That's assuming that this is in fact linear, but pretty sure it is. If they're even gonna ask B. But let's go ahead and prove it, or I guess not really prove it, but show it. Right? Okay. So I'm gonna take some vector x and some vector y from from R3. Let me go define those. Right? So let x equal this vector. So x1, x2, x3. So clearly a vector from Rn, or 3, R3, right? And y equal y1, y2, y3, right? So this is what I have. I need to now prove or show this statement first, right? Okay, so let's take t of x, right? So I got t of x. What is that going to equal? Or yeah, actually, here I'll just do it in like one sort of step here. So what is t of x plus t of y? What is that going to give me? Well, I have to actually use my transformation in order to kind of figure that out. So let's go over here and see what's happening, right? So in the first component, I have x1 plus x2. So because I'm dealing with x right now, I can actually just kind of like almost copy that down. So I have x1 plus x2. And what else do I have? I have x1 plus 2x3. So x1 plus 2x3. And then what else do I have? I have x2 minus x3. x2 minus x3. Okay. So I'm going to close that off, just kind of denoting that this came from this guy right here. So I'm going to add it to t of y, right? So what is t of y? It's basically like the same stuff here, just change out the x's with y's, right? Because we were using these three components for this guy, so we're just going to use these three components for like this up and coming output, right? Okay. So here I got y1 plus y2, right? I have y1 plus 2y3, then I have y2 minus y3, right? And if I were to add these two vectors, because they have 1, 2, 3, and 1, 2, 3 components each, right? So I'm allowed to add these. If I add them, then what do I get? I get x1 plus x2 plus y1 plus y2, right? Because we're just going to add components together, right? Adding the second like row of components, so to speak, we get this y1 plus 2y3, and then we get x2 minus x3, and then plus y2 minus y3. So in other words, right, we actually get t of x plus y. If you're not seeing that though, let's do it a different way, right? So okay, so this is the left-hand side of that equation, right? This was this. Let's go ahead and find this individually and see if they match up, right? So let's go ahead and just kind of compute t of x plus y, right? So let's go, I'm gonna go ahead and just kind of like copy this down just for reference, right? It's gonna be a little easier. Okay, so that's our transformation. So what is t of x plus y? Let's compute that first. So, or I guess x plus y, really. So over here, I'll do that. X plus y is simply equal to x1 plus y1. What did I say x2? I hope I didn't. X1 plus y1, right? X2 plus y2, and then x3 plus y3. Let's draw a better y here, right? So that's my vector in R3. I have to now throw this into that transformation, right? And get something along these lines, right? So I guess it would have been better if I said, if I included that in my crop, right? This is equal to t of x, right? So now instead of throwing x into here, I'm going to throw x plus y into there, right? And then I'm going to get a vector out, right? Okay, so what is this saying? It's saying the first component of the vector plus the second component of the vector. So in other words, this plus this, right? So I have x1 plus y1, and then I have plus x2 plus y2. Okay, let's compare it, right? So there I have x1, x2, I have x1, x2, and here I have x or y1, y2, right? So the first row is looking good. Let's check the second row, and let's close this off. Okay, so what is the second row telling me to do? It's saying, right, I need the first component of the vector plus 2 times the third component of the vector, right? Okay, so let's do that. I have x1 plus y1. It's going to be plus 2 times this. So what is that? What is that really? It's 2x3 plus 2y3. See, I took a 2 here and I just kind of distributed it in, right? Okay, so let's go verify. Does this look like our row or the corresponding row? So x1, y1, 2x3 to y3. It's looking good, right? And then down here, let's confirm the third row. So I have x2, the second component. So I got x2 plus y2. It's going to be subtracted from the third component. right? So distributing that negative, you get negative x3 minus y3. Let's confirm, right? I have a positive x2, I have a positive y2, I have a negative x3, and I have a negative y3. So now I've proven like that first condition, right? So since this is exactly equal to this, I know that t of x plus y is equal to, well, I actually said it in reverse order, but t of x plus t of y is equal to t of x plus y, right? So that was one. Now I have to go ahead and prove this condition right here. Okay, so let's go ahead and do that, right? On the left side, and we're going to use the same x that we defined earlier, right? So I have k times what is t of x? T of x is literally right here, right? So k times x plus, or I guess x1 plus x2, x1 plus 2x3, and then x2 minus x3. What is that really equal to? It's equal to kx1. So basically distributing that k into all my rows, this is what I get. I guess I'll write 2kx3 here, and then kx2 minus kx3. Okay, that's what you get out of this. And that was this left-hand side here. So basically, for notation's sake, I'll say that this is k t of x, right? That's what the left-hand side is equal to. Now, if I can go ahead and compute the right side and get this, then I know that t is linear, right? So let's go ahead and compute that, right? So what exactly is kx, right? If I know that that x is just this, x1, x2, x3, then I know that kx is going to be equal to k x1, k x2, and then k x3. That's the vector that I will be throwing into my transformation and hopefully getting this out of it, right? So okay, we have t of kx. What is that equal to? It's going to be equal to, okay, so I need the first component plus the second component. So first plus second. So that's going to be my first row. So I have kx1 plus kx2. Okay. Is that the same, right? kx1, kx2. We're looking good, right? Okay, so now what is the second one? Second row wants us to do. It wants us to take our first component plus 2 times the third component, right? Okay, let's do that. So first component, kx1 plus what is it? 2 times the third component. So kx3, and we see that kx1 is here, 2kx3 is here. So we're looking good. Now that last one, we just want the second component minus the third component. So second minus third. So I have kx2 minus kx3. Okay, and that's exactly equal to this. So I've proven both cases. I've proven that, like kt of x is equal to tk of x. Or really, I should have said tkx, right? And then I've also shown that t of x plus t of y is equal to t of x plus y. So now I can say something along the lines of, like therefore, t is linear, right? That's what I can say. Now, I was mentioning earlier that there is an easier way to go about this, and an arguably more beneficial way of going about this because it'll help with b, which we'll go over in the next video, right? B. We'll be going over B in the next video. We're going over this now, right? So if I can find some matrix A times x to be equal to t of x, then I actually prove in that step that t is linear, right? So okay, how do I go about potentially finding this A? Now, of course, we already proved one, so I know that there exists an A out there. But how do I find it, right? Even if we didn't do one, right? So just looking at this, how do I find the A? Let's go ahead and look at our transformation again, right? So okay, we have this color, or I guess like this is our output, right? So we have like three vectors, right? We have like x1, x2, or I guess we're dealing with x1s, x2s, and x3s, right? Now, how can I I guess represent a matrix that sort of looks like this, right? I'm dealing with x1s, I'm dealing with x2s, and I'm dealing with x3s, right? How can I represent a matrix A like this? Well, let's go look at what we have. What is in the x1 column, so to speak, right? I see that I have a one, I guess one x1 in the top row, or yeah, one x1 in the second row, but then no x1s in the third row. So what is my first column of my potential matrix A going to look like? It's going to look like this, right? Okay, so 1, 1, 0. So what does that denote? That denotes that in the first row I had 1x1. It denotes that in the second row I had 1x1, and it denotes that in the third row I had 0x1s. Okay, so what is the second column of my matrix going to look like? My matrix A, right? I need to go look at my x2s. This is going to be like the x2 column, right? So I'm going to go look for x2s. In my first row, I see that I have one x2, right? So I'm going to put a 1 here. In my second column, I see that I have no x2s, so I'm going to write a 0 here. And in my third column, I see that I have one x2, right? So I will put a 1 here. And now we have to go ahead and check the x3s, right? So let's go ahead and check that, right? It looks like we have 0 x3s in the top row, or the first row really, right? So we're putting a 0 there. It looks like I have two x3s in the second row, so I'll put a 2 here. And then in the third row, it looks like I have -1 x3s. So I got -1 here. So since I was actually able to find this coefficient matrix that kind of represents the output of my t, of my linear transform t, this alone is enough to say that we have a linear transformation, that t is linear, right? If for whatever reason I'm not able to construct this matrix, maybe what do you call it? Maybe like x1 is quantity squared, right here, then I'm not going to be able to make that the matrix A times the vector x1, x2, x3, because this is what you really need. You need ax to equal t of x. So if x1 is squared now, I'm not going to be able to do that anymore, right? But if everything here is linear, then you should be able to make a coefficient matrix A times a vector x that's in R3 in this case, right? So this alone is actually enough to tell that T is linear, right? And it's actually going to be extremely useful for B. But this video is already long enough. I'm going to cut it here. I hope that was helpful. And if you need anything about this, if you need any clarification, just let me know.